Speaker is Maciej Dunajski from DUMPT, and he will talk about topological solitons from geometry.
Thank you. It's a great pleasure to be here, think back about research, having just done 67 admission interviews earlier this week. It's some work I've done recently, and it's to a large extent motivated by ideas of Michael Atiyah, Nick Manton, and Bernd Schroers in their earlier work on geometric models of matter. And just to introduce the theme, I'll talk about topological solitons, and they are, from a point of view of differential equations, ruled by nonlinear differential equations, hard, often impossible to solve analytically. And my main message will be that if you look at these topological solitons on spaces which are curved, have some non-trivial geometry, then you might actually be able to read off a soliton directly from the underlying geometry of space or space-time. And that will often lead to exact results. So, the geometry will be the solid. I mean, that's the overall message. But I understand that this is the first day of the topological soliton session, and it's not yet quite the session, so that'll give me an excuse to give some overall motivation introduction. I think the subject goes back to an early debate about what particles are and what waves are, so that goes back to early days of quantum mechanics. And I think it's fair to say that in this debate the waves have won. So I'm quoting Max Born because I gave this talk in Wrocław a few months ago. He was a Wrocław physicist, or Breslau at the time. He says, "I'll only say that I'm emphatically in favor of the retention of the particle idea. Naturally, it's necessary to redefine what it means." So if you think about difference between particles and waves, you think of characteristics which you assign to both. So waves have dispersion, diffraction, very important superpositions, both classically and quantum mechanically. Essentially, the Schrödinger equation is linear, and if you take two solutions, add them together, you have another solution. And that's not only a mathematical trick, that has physical consequences if you talk about interference experiments. Particles, on the other hand, they have mass and they have localization. So they either here, not there, but not everywhere. Now, if you then try to turn these characteristics into formalism, you find that mathematics are different. So for waves, you use these superposition techniques that leads to quantum field theory, Fourier transform. Well, then you're faced with infinities, but you deal with them by regularization. And before you know it, you'll do string theory. On the other hand, particles, you find that it's important and interesting to look at fully nonlinear classical field equations, where you don't use perturbation techniques, you try to solve your equations exactly. That if you impose the finite energy conditions on your solutions, leads to certain topological charges. We think of them as some homotopy elements or whatnot, and you use these topological arguments to argue for stability of solitons. Right? So here is a kind of a toy example which I'll be generalizing. Think of a map phi on 1 + 1 dimensional Minkowski space, and so you'll be talking about critical points of this Lagrangian. They'll be static, so phi will not depend on time, and there is a kinetic and the potential term in the Lagrangian. So we define a soliton as a non-singular, static, finite energy solution of the Euler-Lagrange equations. Now, for quantum mechanically, you argue for stable vacuum, so you want the potential U to be bounded from below. Well, let's say it's bounded by 0, and let's also say that the inverse image of 0, that is the set of phi's on which U vanishes, is non-empty. I mean, it's non-empty, but it's not, it has more than one element. Let's say that it's discrete. It could be infinite. It's enough to say that it's finite. Now, you then impose this finite energy condition, right? So you want the energy associated to this Lagrangian to be finite. Therefore, asymptotically, as x tends to plus and minus infinity, you would want phi to tend to one of these numbers. And this is because if it didn't, u would not be 0 at infinity, and that would give you a contribution to your integral, which would make it infinite. Now, from there on, there are two ways to proceed. You can either pick one of these elements of one of the critical values where potential vanishes, and look at small perturbations around it. So then you write down the Euler-Lagrange equations, so expand them in a Taylor series, and the first term in the expansion will be 0 because phi 1 is a critical point, and the second term will, evaluated at phi 1 will give rise to a mass, and you neglect the other terms. And that leads to a linear equation, Klein-Gordon equation, which you interpret as perturbative scalar boson. And that, as I understand, is a standard quantum field theoretic way of dealing with Lagrangian dynamics. Another thing you could do, you could say that at one end of a real line, at x goes to minus infinity, phi tends to phi 1, but at the other end, phi tends to phi 2. So indeed, asymptotically, phi will tend to a value at which potential vanishes. But this sort of configuration that is called a kink, that is well outside the reach of perturbation theory, because you see phi 1 and phi 2 are so finitely separated. And if all you do is you look at these finite perturbations around phi 1, small perturbations, you will never ever get to phi 2. So that's a non-perturbative solution. And there's kind of graphs which go with it. So this is a graph of a potential. I've chosen u to have just two minima at 1 and minus 1. And this is a graph of a corresponding phi. So here we have phi on this axis as a function of x. And it tends to minus 1 asymptotically at minus infinity, tends to plus 1 at plus infinity. So you see that you would then argue that because of these boundary conditions, you don't really care what happens in between, I mean, what the shape of phi is, but because of these boundary conditions dictated by finite energy, this sort of solution is stable, right? Because it will take infinite amount of energy to deform it to a zero solution. Now, the two models I'll talk about will also have these important boundary conditions. It will be a bit more complicated. And but it'll be these boundary conditions which will ensure stability. I mean, there are two mechanisms you can introduce to talk about stability on solitons. One sort of non-trivial topology, and the other one with complete integrability. That applies to solitons like KdV solitons and whatnot. But I think for stability reasons, this first one is much better understood. So the two models I'll talk about are, first of all, static vortices. So the mathematical setup is you have an abelian gauge potential, so one form, and the complex valued Higgs field. Now, the boundary conditions will be such that the gauge field of this abelian gauge potential is 0 at infinity, but the Higgs field is a complex number of modulus 1. Therefore, if you think of a large circle in R2 and representing the infinity, what the Higgs field gives you when you restrict it to this circle is a map from a circle in space to a circle in internal space. Such maps are partially characterized by the winding number, the first elements of first homotopy group, and that you identify with the vortex number, and then you argue that if you have a solution with vortex number equal to 1, then it cannot, because it has to be an integer, it cannot jump to be 0, so that vortex is stable. The second model I'll talk about, that skyrmions, so these are maps from 3 plus 1 dimensional Minkowski space to the total space of Lie group SU2. Now, if you then impose static and finite energy condition on these skyrmions, I'll tell you what the Lagrangian is in a moment, you find that because they're static, they defined on R3, but the finite energy will imply that they really extend to 1-point compactification of R3, S3. So you have maps from S3 to SU2, which topologically is S3. And again, there is a winding number which goes with it. This is now an element of third homotopy group. You can actually calculate it, I mean, several ways. This is one way, using an integral. You have to take a trace of u inverse du cube. That's an integer if you normalize it. And in the context of Skyrm model, so I'll tell you more about Skyrmions, they sort of describe low energy effective theory of baryons. That number is to be interpreted as a baryon number. Right? So what I'll tell you now is how you can construct these vortices and Skyrmions directly from the underlying curved geometry of space. So first, it is this vortex. So it's a abelian Higgs model. And I'll look at them at on a curved background. So the background is a two-dimensional Riemannian manifold, sigma, and that has a metric, and it has a volume form omega, which is also a Kähler structure. Now, in this mathematical context, you think of a Higgs field as a section of a Hermitian line bundle. So line bundle, it was an assignment of a complex one-dimensional vector space to each point, and this abelian potential is a connection on this line bundle. Now, we then write down the Landau-Ginzburg energy functional. So it'll be enough to talk about critical points of this functional because the solutions are static. The coefficient here is chosen to be a quarter, so this is a critical coupling, so that you can follow the Bogomolny trick and complete the square in this functional, and you can then show that the second order Euler-Lagrange equations here are satisfied if this system of first order equations holds. So these are the Bogomolny equations for the abelian Higgs model. The first equation, I'll be a bit more concrete about them in a moment. The first equation tells you that phi is a holomorphic section of this bundle, and the second equation is an algebraic constraint between the gauge field and the Higgs field, right? So they both nonlinear equations. This one because it's a quadratic, and this one because in the covariant derivative you have to multiply phi by a. But let's think about them a bit more concretely. So what you do is you trivialize your bundle. So you choose some local coordinates x and y on sigma, and you choose a complex coordinate z. Now, there is a metric on sigma, but any metric in 2 dimensions is locally conformally flat. That is, you can write any metric on a surface as some function times a flat metric. So here I'm doing it in this z and z bar coordinates. Right? So we've adapted coordinates. Now the next step is you think of this Higgs field. Now we know that it's just a complex number. So it's a map from the xy space, from sigma to field of complex numbers. And you have a polar decomposition of it. There is a real part governed by exponent h/2, like a radial part, and the phase governed by chi. So h and chi are two real valued functions. What you do then is you take the first equation, and so this tells you that you take a kind of d bar derivative of phi plus conjugate of a times phi equals 0. You solve this equation for a, for the potential. So you've solved this equation, and then you substitute the solution to the second equation. And that gives you a very kind of concrete looking PDE. So this is a PDE on the function h. This nabla, this is just a Laplacian, the flat Laplacian on R2. And this equation involves h as an unknown, and it involves omega, which is the curvature of your space, right? That's called the Taub's equation. Now, you would want to solve this equation subject to some boundary condition which will guarantee finite energy. And then, so what you want is, you find you want h to have the following behavior near z equals z0, which is a position of a vortex. So there is a logarithmic term multiplied by 2 times an integer, and then some regular power series expansions. And this number n is the same number I told you about before, which arises from homotopy. To relate one picture to the other picture, so how is it you get this homotopy at infinity? From the integral, you have to use Stokes' theorem and integrate by parts. Now, so I say, what is the kind of simplest space you can think of to solve these Taubes equations, to find vortices? Well, that's obviously, you would think, R2, where the metric is flat. But even then, you find that there are no explicit solutions. So this Taubes equation is not, it's not an integrable equation. You cannot write solutions down. In fact, there's great contribution of Cliff Taubes to prove the existence theorem for vortices for any given vortex number. So you give me an n, and Taubes' theorem will tell you that there is some moduli space of vortices with this number n. Now, the idea I'd like to promote is how can you make this Taubes equation solvable, integrable, so that you can actually solve it and see what the vortices are made. And the idea is this. You have to make some ansatz on h which involves omega, or if you prefer on omega which involves h. So h and omega will not be independent anymore. In fact, what I'm doing is I'm picking omega to be exponent of minus h over 2. And then, if you substitute this to Taubes' equation, you find after some work that it reduces to, well, I mean, the kind of well-known equation in the game is a sine-Gordon equation that describes solitons. This is a similar one with different properties, but also integrable Sinch-Gordon equation. Right? But what you've done here is you've really reading off solitons from geometry, because you're saying if omega is such that omega equals minus exponential of minus h over 2, then, and omega satisfies this equation, then resulting h is automatically a vortex. But you don't have to do anything else to find this vortex, because you just read it off from the geometry of the underlying space. And in that process, you end up identifying this line bundle where the Higgs field takes its values with the tangent bundle to the manifold. And the internal symmetry group U1 becomes just the holonomy group of the metric SO2. And you find that the Chern number of this line bundle, that is the vortex number, becomes the Euler characteristic of your tangent bundle. So just last slide on this vortex, a bit more detail. So one interesting question to ask is, if you've identified omega with h, and h satisfies this Sinch-Gordon equation, what is special about the underlying geometry? Clearly, it's not an arbitrary one, because it's subject to a PDE. And what you find that this, with the kind of signs I'm using, the underlying metric describes the most general constant mean curvature surface embedded in Minkowski space. So this is, mean curvature is an extrinsic problem, but it's what you do here is you take a flat metric in Minkowski space, look for a surface. The surface, could be time-like or space-like. Make it space-like. Calculate the second fundamental form and the mean curvature. The constant mean curvature condition is exactly the Taubes equation. Right? But we started to prove that solutions exist, so this probably may be the most technical part of my talk. Well, you look for radial solutions to this Taubes equation with these boundary conditions. Now, for large R, you find that the equation reduces to modified Bessel's equation of order 0, so that h is proportional to a Bessel function with some coefficient. For small r, again, you can solve the equation exactly, and you find that h is proportional to a logarithm. But now, that game you would play with any vortices on any surface without this ansatz. But the key question in the field is, how do you connect these two constants? So how do you, it's called asymptotic formulas. You see, you have a second order ODE, that's this radial Taubes equation. And you've imposed boundary conditions at infinity, So that kills off one constant of integration. So you would expect the solution to depend on one constant of integration. But you have two constants here, sigma and lambda. So you would think that these two constants have to be related. One is a function of the other. And how do you find this relation of the asymptotics at 0 with the asymptotics at infinity? That, to my knowledge, can only be done numerically for vortices on R2, but in this model I can do it exactly. So in general, you see, if R is neither small or large, you find that this vortex equation becomes an interesting, to some people, OD equal to Paul-Levé 3. And then you can prove a theorem. So first of all, you prove that if lambda is in a range between 0 and 1 over pi, then there exists a vortex solution where with this asymptotic connection formula, so it tells you how sigma relates to lambda. Then you sort of refer to something which was having discovered and put forward by Martin Spade many years ago. So Martin told us that vortices could be thought of from a distance as point particles with some strength. And this strength is essentially a coefficient of this Bessel function at infinity. So because of this exact formulae, you can find what this strength is, and you find that it's 4 root 2 over pi. I mean, it's about 10% more than the numerical value of the vortex on R2. And so this is a one vortex solution, you see, because if you impose the boundary condition at 0 in that range, you find that the vortex number is 1. And you can also study this constant mean curvature surface for this solution, and you find that it's regular everywhere. It has a conical singularity at 0. And that, you know, again, is an interesting theorem to prove from mathematics perspective. It uses isomonodromy theory and some formulae developed by this Russian mathematician I've never met, Kitaev, but very powerful theory he has. There is one more integrable case, where you can relate a vortex to geometry and get an integrable equation, and that has to do with not with constant mean curvature surfaces, but with what's called affine spheres, goes under the name of Cicejka equation, but I'll spare you the details. Instead, I'll move on to the second model. The second model where I think the solitons can be read off from geometry, and that's, well, Skyrm model, but with a twist. So this is a model of nonlinear pion fields. I mean, and that is and the setup is maps from Minkowski space to the total space of SU2. Now, the energy in this model looks rather baroque because it has a sort of quadratic. So you define R, you see, given U, you define an element of Lie algebra R to be U inverse du, and then you write down the energy function or the Euler-Lagrange equations, and there is a fairly standard quadratic term which you would expect from various sigma-type, sigma-like models, but there is also this quartic term put forward by Skyrm, and it is the presence of this term which allows you to evade Derrick's theorem. So you can really argue that there are solitons in this model. And I mean, the kind of novelty, if you used to, as I was before I met this, to soliton models, is that in this case that this Bogomolny bound is never saturated. So in all other topological soliton models I know of, like non-abelian magnetic monopoles or instantons or kinks or vortices, you can play this game but you find that the energy functional is bounded from below by some integer, and then you can look at this interesting BPS configurations where the bound is saturated and the second order equations reduced to first order equations. Now for this model that does not happen, so the energy is always greater than this topological degree. So the equations are second order, nonlinear, very hard to solve. And imposing the finite energy conditions gives you, this compactification of R3 to a sphere, and then you're having done so, you have a topological degree which you identify with a baryon number. Now, because this is a nonlinear model and non-integrable model, you cannot really there are no analytic solutions, and what you do instead is you think of some approximation technique. So still you have to analytical solutions, but not quite the same equations you started from. And here's one kind of method which very nice, I'll be referring to, known as the skyrmion from instant ansatz, and that goes back to Atiyah and Manton. And what you do then is you look for sort of holonomies of Yang-Mills instantons in R4 along some lines. So if you're, the details don't really matter that much. If you know about Yang-Mills instantons, you take one of them on R4, and then you pick lines, straight lines in a fixed direction. So let's say these are lines in R4 directions. And then you look at a holonomy along these lines. So you have these path-ordered exponentials. You integrate the fourth component of the Yang-Mills field. So you integrate over the x4 dependence, which you get only depends on free coordinates, a function on the space of these oriented lines. And because you've exponentiated, it has its values in the group. And then you argue that the baryon number, and that's an exact statement, the baryon number of this approximated skyrmion is an instanton number of the corresponding instanton. It's a nice way of thinking of skyrmions, which uses conformal invariance of instantons. So one thing you can understand in a neat way is why is it the boundary condition is satisfied for the skyrmions. You see, these Yang-Mills equations, they conformally invariant. So you can think of them not on R4, but on the 4 sphere. Now you say if you have lines on R4 in one direction and a 4 sphere projects stereographically to R4, so where do these lines in one direction come from? Well, one of them comes from a great circle under the projection, but the other ones come from small circles. So this map is not an isometry. Small circles are not geodesics on a 4 sphere, but you don't really care. But you see, if you then move to infinity in the free space, these small circles shrink down to a point on the sphere, so that asymptotically your skyrmion is just an identity matrix, right? And there are other things you can do. Now here comes a new idea, right? And this idea about 2 years old. That's why I first heard Michael Atiyah talking about it. This will be goes to Atiyah, Manton, and Schroeder's. They want to think of particles, thank you, as gravitational instantons. So I'll tell you a bit about their idea in a moment. First, let me tell you what gravitational instantons are. So that brings yet another type of structure to it. These are solutions to Einstein equations in Euclidean signature, so with imaginary time. But these are solutions which are a bit like ordinary instantons, so that the curvature is concentrated in the finite regions. And these instantons might or might not have a non-zero cosmological constant. Now, rather than give you a theory, let me give you a paradigm example of such an instanton. So here is a metric, and it's a metric with 4 dimensions. I write it down very explicitly. That's known as tau, a self-dual tau-Bnat metric. R is a radial coordinate, theta, phi, and psi are some angles, but you see that the ranges of these angles not quite standard. This is a solution to Einstein equations with zero cosmological constant. It's regular, although it doesn't look like it is. You see, if R is very small, if R is close to 0, it looks like the first term blows up, but it doesn't. If you perform a micro-local analysis, replace R by R squared, you find that for small r, this metric actually flat. It's a flat metric on R4. For large R, you instead find that asymptotically, your infinity looks like a Hopf bundle, S3 over S2 with Chern class 1 and S1 fibers. So this falls into a class of what's called asymptotic locally flat, or ALF instantons. So these are the definition of those is that asymptotically they look like S1 bundles over S2 with different degrees. This one has degree 1. Now, the model of Atiyah, Manton, and Schroeder's is that particles are gravitational instantons. And you can, I mean, I'm myself, it's an interesting idea. I'm neutral about whether it's true or false. My aim is to make it a bit more concrete. But they, I mean, I suggest you have a look at their paper. It's a really interesting idea. In this framework, the charged particles are the ALF instantons, a bit like that, this or something else. And they identify the charge with a Chern number of the asymptotic S1 bundle. Neutral particles are compact instantons because they have no charge, so there is no asymptotic vibration. And they actually give candidates of what instantons you should be looking at for what particles. So basically, proton corresponds to what's called an Atiyah-Hitchin manifold. Neutron is CP2 with a Fubini study metric. Electron is this Taub-NAT, and neutrino is a round metric on S4. Although when Michael Atiyah last visited a few months ago, he said that actually they seem to be taking this one back. So this neutrino as S4 doesn't really work, but the first three still stand. Now, so you know, they don't really make the model concrete, and I know how can you make it concrete? So how can you construct a particle from a gravitational instanton? Well, you could do it, I think, if you first construct a skyrmion from gravitational instanton and then interpret it as a particle. So here's a procedure of how you construct skyrmion from the holonomy of a spin connection of the gravitational instanton. You take a Levi-Civita connection of the underlying metric, and that takes values in the Lie algebra of SO4. SO4, you see, is not simple. It's a direct sum of two SO3s. And in fact, for most of these instantons, certainly for Taub-NAT, one part of this connection, so one of the SO3 parts, is 0. That is called sort of self-dual instanton. But you have one connection, and that's given to you by the metric. You don't have to solve any equations. That connection you reinterpret as a gauge field on your instanton manifold, and from there you read off a skyrmion. But to do it, you need to pick some lines, some kind of trajectories of some isometries. What would be x equals, x4 equals constant lines in Atiyah-Manton model. So what you do here is use the fact that this Taub-NAT instanton has a large isometry group, and you pick a circle. You pick a U1 inside this isometry group, and you look at the holonomy around the U1. So, I mean, again, some of details. Bottom line is you can, for say Taub-NAT, write down your skyrmion very, very explicitly. You, having calculated this connection, you find some explicit functions of R, and you have this hedgehog-like ansatz for what the skyrmion looks like. You can then look at what three-dimensional space is it defined. So what is the space of this, orbits of the circle action on the gravitational instanton background? You find that this space carries a regular metric. It is a trivial circle fibration over a Poincare disk, or upper half plane, such that the radii of the circles are non-trivial. So this is the space where the skyrmion lives. So in the upper half plane model, that's your H2, and that's how the radius of the circle depends on x and y. So better to visualize this in the Poincare disk model. There you see, so you map this to the Poincare disk, you find that the total three-dimensional space has circles as fibers, and the radius of the circle shrinks down to 0. This is, the plot on the left is how the radius kind of changes between points. It looks like it collapses, it's singular at one point on the disk, but you're not worried about it because this point only belongs to the boundary of the disk. So it's not, although it looks like finite distance on this picture, it's in fact infinitely far, and it's not part of your manifold. And that is as a plot of the energy density of this skyrmion on the disk. And the kind of last bit of formalism is how do you do it for other gravitational instantons? say for this Atiyah-Hitchin manifold. So this is the one which in the Atiyah-Manton-Schroeder's model corresponds to a proton. So there your metrics still have some isometry group. This is an SO3 isometry group. A1, A2, and A3 are some functions of R which you can find, well, by given by elliptic functions. You write down the corresponding spin connection, but with topological degree, you struggle baryon number for the Taub-Nats Kerman. You could find it by integration to be 2. In the Atiyah-Hitchin case, you cannot because of this elliptic functions problem. What you do instead is you think of the baryon number or of the topological degree by counting pre-images. So you have some maps from a space to a Lie group, and you count pre-images of each points, and that you can do using some monotonicity. You find that here this topological degree is equal to 1. So that's the end really. So the message is that some solitons, vortices, fermions, maybe others in different models can be read off directly from the geometry of space-time. And in this picture, the topological charges, like vortex number, Skirm number, baryon number, are reinterpreted in terms of invariance of this geometric invariance of the space-time. So you have characteristic classes of the Levi-Civita connection, Euler characteristic or the Herzebruch number, and that leads to explicit solutions. And perhaps that gives you, in this Skirm model, gives you a way to understand particles as for manifolds. So I'll stop here.
Any questions?
So, did I understand that the baryon number is the same as the instanton number of the Yang-Mills connection?
Yeah.
So it's somehow it's obvious in the original Atiyah-Manton construction, but it's not. The topology is a bit more involved.
Okay, so it's good you say. So to me, it's not. I mean, I don't think it's obvious in the original Atiyah-Manton construction. It is true, but why is it? I mean, it's a subtle argument.
It's obvious to
obvious to you.
Well, I don't know.
But here, it's not obvious, and it's probably also not true. So no, but I cannot make. So you're right. There is an instanton number, and there are these Skirm baryon-like numbers, but the sort of construction to do with conformal invariants and bundles, which make it. Because the point is here that the instanton number is really some characteristic class, like the Herzebruch or Euler number of the tangent bundle, and I haven't been able to make it precise. I mean, it's a very good point, but I don't know the answer to that.
So, you say topological charges equal characteristic classes of the connection. To be asserting that they are equal, aren't you? So you've got a baryon number, you're saying it's equal to...
Well, in the Atiyah-Manton-Schroeder's model, by definition, they define the baryon number to be Herzebruch signature. So it is equal then. Right? Now, I'm constructing a Skirmion. Now, I'm not after the baryon number because they know what it is already. What I'm after is a lepton number because they apparently they don't have an interpretation for it in their model. So I'd like to reconstruct a lepton number from these Skirm charges, but even that I cannot convincingly do.
Just a comment that what you showed as Taub's equation,
Yes.
It's known in plasma physics as Grad-Shafranov equation, and it's a condition of stability of two-dimensional MHD configuration. Except you have one particular function there, which is 1 minus e to h, and for any function of h on the right-hand side of that equation,
So this is right. That's the equation.
Yeah, that's right. So you have one particular function, which is omega minus omega e to the h, but for any function here of h, that gives you an equilibrium of MHD two-dimensional equilibrium if you interpret h as the flux function of the magnetic field.
I see. I didn't know that.
But Maciej, you missed out the delta functions on the right hand side, right?
No, no, because I say that I'm only interested in solutions with this asymptotics. I think I can do it like that. I can write Taub's equations with 0
Okay.
if I write that.
All right.
Can you say something about the spin of these particles that you get as manifolds? And whether you can have massless particles with helicity also?
Well,
Your final
I'm far off from the actual particle interpretation. I can just repeat what I understood from the particles from gravitational instanton models. So electron spin. It's not clear to me how Attila, Manton, and Schroeder's read off the spin exactly from their model. Nick Manton is at the back, so maybe he can tell us, but I don't know.
the spin, I think, probably showed that you could quantize it as a fermion, but also to get it massless and to get it with some handedness, that seems a little hard.
That's right, and I think they say exactly that in their paper, and they list it as an interesting open problem to study.
Okay, let's thank Maciej again.